Hey scholars, good to be back with you. In this lesson I want to go over something called parabolic approximation. This is another way of solving problems of a single variable, and there are extensions that work on multivariables. For right now we'll go with single variables. Now, one of the things engineers do a lot, technical people everywhere do a lot, is we take a problem we don't know how to solve or find is too cumbersome to solve, and we approximate it by a problem that is solvable or is easily solvable. And then we keep doing that over and over again until the approximate problem pretty much matches the original one. This is what's going on here. So what we're going to do is we're going to imagine a curve, and we're going to take a real simple one here. Maybe the lifeguard problem. Okay? Remember the lifeguard problem, x star was 87.208 meters. Okay. Now, the whole game here, remember, is that we're trying to find the minimum value of a function without knowing what the function looks like. We know how to calculate it, but we don't have a picture of it. In order to draw a picture, you have to evaluate the function a whole bunch of times. For our problems that we're doing in this class, these sample problems we're using as learning exercises, well, calculating it a whole bunch of times isn't very hard, so it's easy to draw these. In practical problems, and I don't want to say real world, I hope what we're doing here is the real world, but in industrial problems or problems of scientific or engineering interest, calculating the objective function can be a very expensive thing to do. It may take hours of computer time to calculate the objective function even once. So we want to be able to find the minimum of the objective function without calculating it too many times. No more times than we need to. So remember that motivation, even though what we're doing here is computationally pretty simple. So we have an equation, and if you remember, for our variable lifeguard problem, this is the objective function. Okay, and that 2,500 is just 50 squared, okay? So we've got that. Well, that's very much not a parabola. Remember what a parabola looks like? Let's say we'll call P of x is ax squared plus bx plus c, okay? That's just the general form. It's called a parabola or a quadratic equation. And this is just a second order parabolic equation. Okay, this is really easy to solve. It's very, very simple to find the minimum of that, and I'll show you here in a second. So if I could pick 3 points along this curve, put a parabola through it, just write down the minimum of that parabola, and then go check to see if my objective function has gotten smaller, and then reapproximate a couple of times, I might be able to get to there pretty quickly. Let's see how that might work. Let's pick 3 points. 0, 10, and 20. Okay, now I'm not going to write this out by hand. I'm going to go, when I get to the point where we're doing number crunching here, I'm going to switch back over to MATLAB most likely. So but we've got those. We'll figure out f of 0, we'll figure out f of 10, and we'll figure out f of 20. From that, we're going to draw a parabola that goes through all 3 of those points. We're going to find the minimum of that parabola. Now I said you could do it by just writing it down. How would you do that? Well, let's see. If p of x is ax squared plus bx plus c. Remember how you find a minimum or a maximum? You set the derivative equal to 0 and solve. What's the derivative of p? P prime, and that's the same as dp dx, is 2ax plus b. All right? Set that equal to 0. Well, geez, it looks like x star is going to be negative b over 2a. If I know what a and b are, I can just write down the minimum. Now this only works if the curvature is positive. It works if there is a minimum. This equation is either going to have one minimum or one maximum, or if it's a straight line, if that number right there is 0, it doesn't have either one. But let's just say this number here isn't 0, so it has a minimum or a maximum. For a minimum, okay? P double prime, which is the curvature, has to be greater than or equal, or not even greater, equal to, just greater than 0. It has to be positive. Positive curvature means the curve goes up like this. Now, I'm going to draw probably the silliest thing I'm going to draw on the board, probably for the whole class, but you're going to remember it. How do you know the difference between positive curvature and negative curvature? Well, that curve has positive curvature and that has negative. So if we make that a face, that's positive curvature. That's negative curvature. Once again, this is really stupid, but you're going to remember it now, aren't you? Get this out of the way here. Okay? So we got to know that our parabolic approximation has positive curvature. It's got positive curvature. That means there is a minimum. We can just write it down. So let's talk about what positive curvature would look like. If P is ax squared plus bx plus c, then P prime is 2ax plus b, then P double prime must be 2a. Well, if a is greater than 0, we're good to go. All right, so that's where we're going to go with this. So how do you go from there to a parabola? Well, here's how this works. I'm going to write down 3 equations, and this is what they're going to look like. Can I call it, just for simplicity, can I call that F1, F2, and F3, and I'll call that X1, X2, and X3, because if I don't do this, it's going to start getting really cumbersome. But if I can do that, let me clear out some more real estate here. Okay, well, we already know that the general form of a parabola, P is ax squared plus bx plus c. All right. Well, if I'm going to fit a parabola through those points, that means the same equation has to go through those 3 points. That means F1 must be ax1 squared plus bx1 plus c. That means F2 must be x2 squared plus bx2 plus c. And I'll get my head out of your way in a second here, as always. It's 3 squared plus bx3 plus c. Okay? All those things must be true. For the parabola to go through these 3 points, I need to be able to pick those points and figure out what that is. Well, let's talk about, I got 3 equations. Now, the fundamental rule of algebra, fundamental theorem, I think, is that if you have 3 equations, you can solve for 3 unknowns. All right? So, what are the unknowns here? Do we know F1? Yes, we do. We will have figured that out. Do we know F2? Yes. Do we know F3? Yes. Do we know A? No, we don't. Do we know that? Yeah, we do. We know that. We don't know B, and we don't know C. And that's true for all 3 of those equations. So our unknowns are A, B, and C. They're not X and they're not F. We know what those are. So I've got 3 equations, 3 unknowns. Those are my unknowns. This should be easy, right? Well, how are we going to do that? Well, you could start back substituting and all that kind of thing. That definitely works. There's a cleaner way to do this. If I write this out as a matrix equation, if you haven't seen how to do a matrix equation, if you've never done matrix algebra before, it's an entire field of mathematics. Okay? There are whole books on what's called linear algebra, which is matrix algebra. It's a field of research that I think is still quite active. Our little corner of it, the tiny little corner of it that we're going to use, is basically notational. It's basically a simple way to write out linear equations. There's a lot more to it than that, but the part we care about is that. So here's what I'm going to do. If I want to write this out, let me see if I can get, oh, we got plenty of room. Okay, I want to write this out. F1, F2, and F3. I'm going to write those out as a vector. These braces here, that means vector. And then I'm going to write out a list of numbers. And these are numbers. These are not unknowns. Let's see, I'm going to make sure I do this right. 1, x2 squared. I'm sorry, I'm doing this wrong. x2, 1, x3 squared, x3, and 1. Okay? There's a list of numbers. These are coefficients. These are not variables. These are numbers because we'll know what those are. That one's 10, that one's 20, that one's, or I'm sorry, 0, 10, and 20. Those are numbers. Here's the things we don't know. A, B, and C. This is a matrix equation. And what this lets us do is write it out this way. F equals, and I'm going to call these x's. Well, this is x times, I'm going to call that just C, because that's a list of, let me do it this way. I'm kind of pausing because this is really unusual notation. I'm stuck with it because of how I wrote this down. F is it stands for that vector. X stands for that list of, or that box of numbers. Normally X stands for variables. Here X stands for actually for numbers. Normally C would stand for variables. Here it stands for constants we're trying to find. And what we would do now, with that matrix equation in hand, we can do this. And that's a capital F I use down there. The nice part about this is true no matter how big those lists are. If this is a list of 3 and that's 3 by 3, that works. If this were a list of 20 and that was 20 by 20, this would still work. And the thing is, when you write it out in matrix notation, computers love it. MATLAB stands for Matrix Laboratory. Well, that's a matrix equation. This is exactly what MATLAB was designed to do originally, and it's pretty good at it. So we're going to stop right here, and I'm going to go to switch to MATLAB, and I'm going to show you how to find C, and I'm going to show you how to superimpose the resulting parabola over a plot of our objective function so we can find the minima by successive approximation. So here we go.
Okay, here we are now in MATLAB again, just like before. And we're going to go ahead and find the minimum of the objective function for the lifeguard problem using sequential parabolic approximations. Now you can see over here in the command history window, I ran this problem a couple of times before I turned the screen capture on, so you can see all the commands and stuff I used before. And I'll recall some of those so you don't have to watch me sit here and type them out again. So to start, let's define the objective function. Now in the past I've used the letter F to stand for the objective function, but I'm going to use F for some other things, so I'm going to go ahead and call it OBJ for objective function. There it is. Now two things to notice are right there, the 2500, that's just 50 squared. And there's that dot again we've used before that says we're doing a vector calculation step by step or element by element. It's not a dot product or a cross product. And the reason I did that is when I left that out, MATLAB gave me an orange warning message saying it would run faster if I put that in. Now when you go ahead and execute a command and you see orange letters come back at you from MATLAB, that's just a warning. That's not an error. It doesn't mean anything's necessarily wrong. It's just something to watch out for. If you get back text in red, that's an error. That means something's wrong. Something's irretrievably wrong. It couldn't correct for you. So anyway, there's the objective function. Now let's plot it out using easy plot again. Now, I know something you don't know. I know that after the first approximation, the estimated value of the minimum is above 100. I didn't know that before I tried the problem with these starting parameters. But it is a little above 100, so I'm going to plot out to 150 just to make sure we don't get lost. So there it is. Now, as before, let's move this over and put this over here, so we can see the plot while we work on it. I'll make that a little bigger just so we can, there we go. Now we'll be able to see what happens to the plot as I execute commands here. Now I'm going to want to put some more stuff on this plot, so I'm going to say hold on. Now I already know that the objective function minimum is at 87.208 meters, so I'm going to put that on there. You can see it shows up there in my workspace. Let me move this over since I don't really need that. And I'm going to say F star, which is my current current estimate of, well, this is the exact minimum, is going to be OBJ of X star. I'm going to let that echo. Well, I guess I don't need to echo to the screen. There you go. And it's 40.166, which is the number we had before. Let's go ahead and put that on the screen over here. Let's actually put that on our plot. By the way, let's turn the grid on. Okay, so we've got that. Now, if I wanted to change the grid spacing, I can, but for right now, that's okay. And let's say plot x star, f star. Those are the x and y locations. Now, these are normally lists of numbers, but since it's just one number, it'll just plot one point. And what you can do, one of the handy features of MATLAB is you can tell it what you want to plot. And if you go into the help file for the plot command, it'll tell you what all these letters here mean. You have the choice of using several different colors, and B stands for blue. And you can use whatever marker you want. And I want my marker to be, actually let's make that a plus, okay? And it'll put a plus right at the minimum of the objective function. It'll make it blue. So there it is. Now maybe I want that to be a little bigger so it shows up. I can just double click on that marker, and of course it put it somewhere else. There it is again. And the marker is a size 6. Let's move it up to size 10, and let's maybe make it a little, the line width a little higher. So I'll close that out. So now I've got that nice meaty plus there, so there's no mystery about where the exact minimum is for the objective function. It's right there. And I'm pretty much maximizing screen. So there we go. That looks good. Let's uncheck that. So there's the minimum. There's the target. That's what we're trying to hit. So let's go back over here now, and let's make ourselves a starting point. We'll call x1 is 0. And I think I have this, yeah, I'll just pull that back up. I told you x1 would be 0, x2 was 10, and x3 was 20. Those were the first three numbers I were going to pick. So there's that. All right, so whoops, that's not what I wanted. There, put f equals. There we go. So I'm evaluating the objective function at x1, x2, x3. All right. So there they are. Now I need to make that x matrix, and that's capital X equals. By the way, see those semicolons there? Those are line feeds. Everything that appears here is a line, and then the semicolon means it's a new line. So that if you go over to here, that list of numbers is actually a vertical list. Every one of these is a new row, and you can see that it lists out as a single column with 3 rows in it. When I do this, I need 3 rows and 3 columns. So there's the first row with the individual entries separated by spaces. Semicolon means that's a new row. So there, I get this nice little matrix. Okay, last thing I want to do is say C equals the inverse of x times f. That's what I wrote out there on the whiteboard a little earlier. And so there's our values of C. Now, we're going to get into a little bit of a bookkeeping problem here. That's C1, that's C2, and that's C3. Okay. So when I want to define my approximating parabola, that's what it looks like. It's C1 x squared C2x plus C3. That's really A, B, and C as I had it on the whiteboard, but it's tough to, in fact, I'm not sure how to make that come out assigned to A, B, and C. If you really want to know, I'll figure it out. I got a couple ideas in mind. So there it is, right there. So I've got that. Now what I can do is I can do easy plot, and I can put P right on top of the curve I have already. So there's our estimate of the parabola that is our estimate of that curve right there. Well, it's not that close past here, but up to there, it's actually pretty close. Okay, it's up to there. It's not a bad approximation. The approximation starts to fail here, but let's do this. We know that x star is equal to minus b over 2a, so there it is right there. There's our estimate, is 116.9132, and I told you it was a little bit outside our the range we've been using before. Remember, the algorithm doesn't know this doesn't make physical sense. It only knows that it makes mathematical sense. So that's all right. So let's make f star now evaluate the objective function at x star. There we go. And now let's plot x star comma f star. And now let's make a blue dot. And it'll show up on this curve somewhere. There it is. Now this is in line vertically with 116.9132. So it's the same x location as the minimum there. It's just now up on the original objective function. So what do I do now? Well, I know that's going uphill. The way I know it's going uphill is I can figure out the slope, and I could evaluate the slope at our new estimate of x star, and I would know it's going uphill. So I know I've passed some minimum somewhere. Because of that, I'm going to do this. Minus 20. Y1 is going to be, I'm sorry, x2, not y1. x2 is going to be x star minus 10, and x3 is going to equal x star. Okay, so I've picked points there, about there, and about there. Now these are pretty close to the minimum. I bet the next curve is going to go pretty closely through that minimum there. It's going to approximate it pretty well. So I've got that. Let's see here. X star, my x vector is now going to equal, I'm sorry, the x matrix is going to equal that. F, I need to know that again. So there it is. I've recalculated that. Now I need new values of the coefficients. Okay, that looks good. We'll execute that. And now I'm going to recalculate my approximating parabola. There that is. Let's do this now. Let's easy plot. Go to easy plot again and plot our parabola again. Now this is the same command I executed before, but since I've recalculated the values for the definition of the parabola, that'll give me my new estimate. And there it is. Okay, let's fix a few things here. Let's make this. Now it's gonna change this, but for y-axis limits, wow. Let's make this go from 30 to 80. Okay, that's good. Well, let's get rid of that. Let's go ahead and make that curve right there. Let's make it red maybe. That's easy to see. Okay, there it is. Okay, so now we've got and I'm going to uncheck that so we can see. Now look at the blue that was our original, our exact objective function, and that red is now our approximation to the objective function, and it's awfully close everywhere. You can hardly see the blue line anymore. Let's do this. Oops. What I can do is I'll make that bright blue, make it a little bit easier to see than that pastel blue, and I'll make the line width really wide. And uncheck that. So you can see right in there, it's really close. It's only out here that it starts to diverge again. So let's do this now. Let's calculate our new value of x star and our new value of f star. There it is. And let's plot that again. Let's put another, maybe rather than a blue circle, maybe let's put a red circle at our new estimate to go along with our red line we just drew. Look at that. It's really, really close. In fact, how close? Let's do this. Let's just zoom in, and I'll zoom in some more. There. Let's just do this. There. It's awfully close. The exact answer is 87.208, and I'm almost at 87. I'm 86.969 pretty much. So that's it. That got us exceptionally close in two objective function evaluations. Or I'm sorry, two parabolic approximations to the objective function. If we wanted to go a little closer, we could. The thing now, though, is that step size of 10 we were using, let's see, up there, That's probably too close or too big a step. We probably need to go to something smaller than that. But you get the big idea here. We started out by approximating the objective function with a parabola, got an okay but not great approximation using our first iteration, and then starting at that first iteration, went back and ran the algorithm one more time, and in our second iteration got exceptionally close. Now that's a little more than 0.2 meters away. Well, that's about how big my foot is. In fact, I'm not sure my foot is that big. Yeah, my foot's smaller. It was larger than that. So that's practically as close as we need to get to this problem for physical purposes. So there you go. There is sequential quadratic approximation.